Hi, everybody. Welcome to Physics C Mechanics. My name is Angela Jensvold, and today we're going to review impulse. So the first thing I want you to do is pay attention. I have three solid spheres. I have a green one, a yellow one, and a red one. And I'm going to go in that order so you can remember it's like a stoplight, green, yellow, red, okay? So make your observations and try to remember because I'm going to ask you some questions about it, okay? So first, watch the green sphere. And then the yellow, and then the red. Okay, I want you to answer some questions about it. I hope you were able to see that the green sphere, watch it one more time. It's stopped. Okay, so I'm going to put up a question and I'm going to give you a couple of minutes. What I want you to do is rank the impulse on each sphere, but more importantly, I want you to justify your answer. Okay, so I'm going to give you a minute or two to do that, and then we'll come back. How'd you guys do? I didn't time you, so I don't know how much time you've had, but I think we should go over it. Okay, so let's review. I think I did green first. I said it was for you to remember, but maybe for me. Okay, so I think we did green. Okay, so we had a green ball and it was launched with some speed v, and then it kind of got embedded in some plastic. So I hope you're able to see that on the video, that it stopped and got sort of gently stopped by that ball of plastic. And then I had a yellow ball and it stopped quite abruptly on a piece of tape. Okay, and then I had a red ball and it was moving with speed v, and then it hit the side of the pool table and it bounced back. I hope you noticed that I was able to launch all three spheres with the exact same speed. Amazing. Okay, and they all have the same mass. All of these spheres have the same mass. So your job was to rank the impulse, right? So impulse is change in momentum. And I put the vector symbol quite intentionally because if you forget momentum is a vector, you're doomed. Okay, so I hope you guys included the direction in this. Okay, so let's do the green one first. Well, impulse is change in momentum, so that's final momentum minus initial momentum. I keep writing that symbol to continue to remind you. What was the final momentum of the green sphere? 0. What was the initial momentum? Well, if I call up positive, which we could do that, then it would be, we're subtracting the initial momentum, which was mv. So that impulse is negative mv. What that means is there was a force downward or toward the bottom of the screen on the sphere. Okay, now let's do the yellow one. So P final minus P initial equals, okay, what is the final momentum of the yellow ball? The one that stuck to the tape abruptly. That was 0. And then its initial momentum was identical to the green one because I was able to launch it at exactly the same speed, mv. So the impulse on the yellow ball was negative mv. Okay, and then for the red one, you would do P final minus P initial. What is the final momentum of that red ball? Well, it's going down at a speed v, but the velocity is negative v. So it'd be negative mv minus the initial momentum of that red ball is going up. So it'd be positive mv. So, oops, forgot my 2. So the total change in momentum is minus 2v. So, I mean, we're just going to compare the magnitudes. So if we were to rank them, if we were to rank the magnitudes of the impulse, it would be the magnitude of the red impulse is bigger than the impulse on the green one, and that's equal to the impulse on the yellow one. That's interesting, isn't it? So I'm just thinking the green situation is the equivalent of having an airbag in your car, right? Where you stop slowly, right? And then the yellow one is like kind of like YOLO, no seatbelts today. We're just going to let the dashboard stop us. Okay. So from our calculations just now, if you have an airbag or if you use the dashboard to stop you when you get in an accident, it's the same impulse. So are we just wasting? Is this some kind of a scam that for all of this advanced technology in our cars? Is that what this is about? is what we have on the screen the whole story? And I don't think it is, because there's something else. Impulse is also average force times the time over which the change in momentum takes place. So think about, we know that change in momentum is the same for all 3 spheres, right? But look at the green one, or we're really just comparing the green and the yellow right now. Okay, so the green one had, did you notice that it stopped in like a pile of plastic, so it came to rest over a longer period of time? So the time for the green one is longer, which means the force was smaller. Oh, small force is good if you're in a car and you get into an accident, right? Then the yellow one, it stopped very abruptly on that piece of tape. So the time was small and the force was big. Those are like people who don't wear their seatbelts, right? So to me, the change in momentum is the same, right? And I'm not in any rush to come to rest. So I would choose if I had to choose, I would use an airbag so that the force would be smaller. Interesting also that the red sphere, when it bounced, it had twice the change in momentum. Okay, so maybe if you guys have been on bumper cars, you know quite a jolt it is when you bounce against somebody. All right, we're gonna look at 5 learning objectives today. Here are the main ideas. Okay, impulse is, sorry, not impulse, momentum is mass times velocity. And can I just circle this? Momentum is a vector. You got to remember it. You got to remember that momentum is a vector, okay? This is Newton's second law, isn't it? Because, what does this say here? It's the rate of change of momentum, right? So it's d of mv dt. So if mass is constant, it's m dv dt. What is dv dt? Oh, so that is Newton's second law. Interesting. Okay, so force is the rate of change of momentum. Just want to plug in before I forget. Anyway, that's Newton's second law. And then we have impulse, which is if you have a constant force, it would be force times time, or you could do an average force if you want times time. But if it's a variable force, like a very complicated force, then you would want to integrate the force versus time to get the impulse. Okay, now look at Newton's second law. Look over here. You know what? It should really be sum of the forces on an object or system of objects. Okay. If the sum of forces on an object or system of objects is 0, what would that mean? Look at that equation. If the sum of forces is 0, the left side of the equation is 0. So that means the right-hand side would be 0 as well, right? So that means the rate of change of momentum is 0. In other words, momentum is constant. So momentum is conserved if the sum of forces acting on an object or system of objects is equal to 0. And then the total momentum of a system is just the vector sum of all the momenta of the individual particles. Okay, we already did A and B. I hope you remember. I hope you have fond memories of doing A and B last week. We calculated the mechanical energy was 7 joule. Whoa. Try that again. 7 joules. Okay, so now can you try C and D? Okay, so if you remember, mechanical energy is kinetic plus potential, right? So 1/2 mv squared plus 4x squared. And you're investigating this situation at 0.6 meters. So what you would do is say 7 is equal to 1/2 of 3 kilograms times v squared plus 4 times 0.6 meters squared. And if you solve that for v, you'll get 1.9 meters per second. And they're asking for the momentum at that position. So it would be mv. Well, it's just magnitude actually, so we don't need the vectors, but 3 kilograms times 1.9 meters per second should give you 5.78 kilogram meter per second. And there's no special name for that unit. You just, I don't know why. Calculate the magnitude of the acceleration. Okay, well, you know what? Do you remember that force is negative du dx? That was from last week. So if you differentiated our potential energy function with respect to position, you would get negative 4x. Okay, and we know acceleration is sum of forces over mass. This is the only force that's acting on the object. So it'd be negative 4 times 0.6 meters over 3 kilograms. And if you plug that in, you get negative 1.6. I don't know how that happened. 1.6 meters per second squared. Okay. Okay, try this one. Okay, so we want to know the speed, right? We know that change in momentum is integral of f dt, right? So that would be m delta v is equal to the integral of 0.5 t dt, but it started from rest. So that means v initial is 0. So it'd be mv final equals 1/4 t squared, right? So v final would be t squared over 4m, which is 16 second squared over 20. It would basically be 0.8 meters per second. Okay. Okay, try this one. So this one is basically kind of a redo of the red sphere that we did in the beginning, but it's worth doing because it's so important. It hits the ball with the speed of the initial, and it leaves the floor with the speed of V final. Look at this word, speed, speed. What does that mean? It means that they're going to make you realize that you have to not just consider speed, but velocity. Okay. You're going to have to put a direction on this because they're asking you for the impulse, right? So impulse is change in momentum, which is mass times change in velocity. So it would be mass times V final. So I'm saying up is positive. So V final minus, what is the initial velocity? Negative VI. So the answer is M times V final plus V initial. That's V initial. Oh, I just cut myself off here. Well, I'll do it again. M times V final plus V initial. How's that? Better? Okay. Try to pay attention to that. Okay, try this one. Oh, this says rest. Okay, so you've got a ball of mass m, drops from a height h, and then it goes right back up on the way up, goes to the same height h. Okay, what is the average force? Okay, well, we know average force times the time over which the force is exerted is equal to the change in momentum, which is m delta v, right? So to get the average force, you would need the mass, we've got that. You would need the final velocity and the initial velocity, which we could figure out in terms of the given. We could use energy conservation and we could get v final and v initial in terms of h, no problem. So our numerator, we have everything we need, but they didn't give us the time. So this was a trick question. I hope you got that. So you just can't do it. They didn't give us the time, so you can't do it. Trick question. Okay, we're gonna do a hard problem now, okay? So fasten your seatbelts and be patient and try this one as best you can. I'm only doing parts A through D. There's a second part. So this page is like medium difficulty. See how you can do. Okay, how'd you guys do? This part is like kind of medium difficulty. I circled all of the givens, okay? They've given us 4 quantities, so all of our answers should be in terms of those 4 quantities. Let's start with A. Determine an expression for the time required. Well, we know that impulse is average force times the time interval, right? So if we want the time interval, we should do the impulse, which they said is JP, divided by F average, which they defined as F average. Okay, that wasn't so bad. Part B, determine an expression for the mass of the projectile. Okay, so for the mass, we're going to have to say m delta v equals the impulse, right? That's just a general equation, and we want to find mass. So mass would be the impulse, which was Jp. And what is the change in velocity? Well, the final velocity is Vx, and the initial velocity is 0. Okay, so it's just minus 0. Remember, this is when it's being launched. It starts at rest, and it gets launched from this thing at a speed of Vx. So this question is when it's being launched. Now, okay, that was part B. This was A. Let's do C. Now you launch it into a block of wood, and it can't move. Okay, maybe I could draw like Can you see that? And there is a, no, you can't see that. Oh, yeah, you can see that. Here's your block of wood. Okay, yeah, you can see that. Okay, so basically this projectile, which I'm going to call a point particle, I'm going to draw it here, and it went into the block a distance d. That's how far it went into the block, okay? Determine an expression for the work done stopping the particle. Okay, well, what we can do is figure out how much energy has been dissipated. So why don't we do that? So I'll put energy dissipated is equal to E final minus E initial. Well, the final energy is 0. It completely stopped. Okay, and there's no other forms of energy. So you just want to do minus 1/2 m Vx squared, right? But we can't leave it in terms of m. That wasn't a given. So we're going to substitute our expression for m for part B into here. So it would be negative Jp over Vx times Vx squared all over 2, right? Okay, so then one of these is going to cancel, and we get negative JPVX over 2. Okay, that's how much energy was dissipated when the projectile went embedded into the block. Okay, now D, derive an expression for the average force exerted on the projectile as it comes to rest. Okay, so for this, you know, energy dissipated would be, it would be negative FB, that's the force of the block, times how far it goes. I'm not calling that the work. I'm calling it the energy dissipated, okay, is equal to the answer from the last time, right? So negative JPVX over 2. And then we're looking for FB, right? So FB, well, what happens? The negatives cancel. And then we get JPVX over 2D. Okay? Okay, so we finished the first 4 parts, and they weren't easy. They were, you know, substantial. I hope you wrote down all of your answers because you're going to need it for the next page. Okay? So keep your answers so you can do the next part. Okay, so this part is hard. Okay, I'm just telling you. So if you have difficulty, it's okay. So do your best, parts E and F. Okay, how did you do? It's a lot, right? We've got how many different Ds? 3 Ds? Yeah, it's okay. So we just have to, I tried drawing a diagram so I can remember, okay, dn is how far the projectile goes in the block. Capital D is how far the block moves sideways. And then there's another D, is there? Oh, D, regular old D, is what we found before, and that's how far the projectile went into the block when it was clamped. Okay, okay, we can do this. That's fine. Okay, derive an expression for dn. Derive an expression for how far the projectile goes into the block now that it's not clamped to the table. All right, we know that the energy dissipated, we have two dissipative forces. They're going to dissipate energy. So one of them is going to be force of the block, dn, and the other one is friction from the table, and we'll call that, and that acts, the distance over which it acts is a capital D, okay? And how much energy did it dissipate? Well, it stopped, so it's 0 minus 1/2 mvx squared, okay? So the initial energy of this whole system was 1/2 mvx squared, okay? Where did that energy go? It went into internal energy of the block, went into sound. And that's why I'm not calling this work done. Okay. I'm calling it the energy dissipated because the work done by these forces is not calculable. You can go back to the work video and watch that if you want to get an explanation. Okay, so what are we trying to get? dn. Okay, but wait a minute. 1/2 mvx squared. I wrote it down from before. First, can I please cancel these negatives? Okay, now 1/2 mvx squared from before, we calculated that was jpvx over 2. Is that going to help us? I think that's going to help us. Yeah, okay. So we have fbdn plus ftd is equal to jpvx over 2. Okay, but in part D, I hope you still can reference your D. We found that jpvx, I'll write it over here in part D. Okay, so I just want to say in part C, we found that 1/2 mvx squared was equal to jpvx over 2. Okay, that's how I justified putting that on the right side. And then in part D, we found that jpvx equals 2dfb. So I'm going to justify plugging in 2dfb for jpvx. Okay, I hope you're with me here. So the right-hand side just becomes FBD, right? Okay, and we're trying to solve for dn, so we can do that. dn is equal to, oh, I think I need to make another substitution. Yeah, okay. So I think I'm not quite ready to solve yet. Okay, so FBDN, oh, this is fine, I was fine. Okay, so DN is equal to FBD minus FT, capital D, over FB. Is that legible? I'm going to write it bigger down here so you guys can see it. FBD minus FTD over FB. And then I'll erase this ugliness so it looks good. Okay, all right. So that was E. Now we're going to do F. Derive an expression for the same thing, but in terms of masses. Okay, so this is a collision, right? And they're saying it happened instantaneous, so the frictional force is negligible. So basically that justifies our use of conservation of momentum. When is momentum conserved? When the sum of forces acting on a system of objects is 0. So what they're arguing is that friction force is negligible. What's a better argument is that the forces, the internal forces of the collision are way bigger than friction. So you can just neglect friction because it's small in comparison. But anyway, we're going to conserve momentum. So what we have initially was mvx, and then they stick together, right? So you get the final velocity of the system is mvx over m plus capital M. Okay, so now we've conserved momentum, and we have the final velocity of the projectile once it's embedded in the block and they move off together. Okay, now what we want to do is find an expression for the distance that the projectile went inside the block. Okay, so what we're going to do is we're going to say the energy dissipated is equal to the frictional force of the table times d, because our system is the projectile and the block together when they're moving. So the only external force on that system is the friction between the table and the block. So FTD is equal to, I mean, technically this would be negative, and you lost how much energy? 1/2 of, the masses are together now, and the final velocity is mvx over m plus big M squared. Okay, now, so we've got that, and I think we can cancel some things here. So okay, first what I'm gonna do is I'm gonna cancel these negatives, make them positive. So I get FTD is equal to, I'm gonna rewrite this as 1/2 mvx squared times m over m plus m. I hope I did that right. One of these m plus m's canceled. Yeah, I think that's right. Okay, but we know that 1/2 mvx squared is jpvx over 2 from the front side. Let me go up to the top and I'll highlight it for you. Remember, it was from here in part C. So we're going to substitute that. FTD is equal to jpvx over 2. And that is also equal to, if you use our results from D, it would be D times FB. FB times D. So that is equal to, or maybe we're good on that one. Go back to black so you guys can see. Okay, so that is, that's what we have from there. And then if we go back up to our answer from E, we can rewrite FTD. So I'm going to solve this. Oops. FTD is equal to FBDN. Well, that should have been a minus. Okay, I think I'm skipping too many steps. So let me just multiply through. FBDN equals FBD minus FTD. Okay, and I'm solving for FTD. So it would be FBD minus FBDN. So then, so this yellow thing is equal to FBD minus FBDN. Let me make sure I'm on the right track before I keep going. FTD. FBD minus M plus M. Oh, I didn't substitute in. Shoot. Okay. Let me go back. I forgot to substitute in my the rest of that expression. I wonder if you guys caught that. Do you see how I forgot the M plus M? The M over M plus M. Did you guys notice that? Okay. There we go. This is a Vx. Okay, but remember, all right, so we have FBD minus FBDM equals M over M plus M times. Okay, so then now I'm running out of room. Okay, I guess I'll try green. I'm running out of colors. Okay, FTD. So I think what I'm going to do is I'm going to share my whiteboard, and then I'll be able to write neatly so we're not going crazy. Share whiteboard. Okay, I hope you guys have a nice clean screen now. Okay, so I'm going to say, just do black, you can see nicely. Okay, I'm going to go back. We have MFBD over M plus M equals FTD. Okay, and then you get MD over M plus M is equal to DN. So then you get DN is equal to D times 1 minus M over M plus M. I think I might be missing an FB over here. And then you can cancel them. FB, FB, FB. And then, yeah, I think that's right now. Ooh, wow. I told you guys that was going to be hard, didn't I? I warned you. Okay. Let's go back. Okay, can you guys try this one? This will be easier, okay? Okay, that's all I'm going to give you because we're going to run out of time. And I want to make sure I go over this. So the block has a force of the earth acting down on it, and it has a normal force of the slab acting upward, and then it has a friction force from the slab acting to the left. Now the slab is more massive, so I guess I'll draw a bigger vector, force of the earth on the slab. And then it also has the block pushing down on it. So it has a big normal force of the table on the slab. Now, I have a feeling a lot of students, when they took this question, it's an old AP question, that they probably missed this, but I'm going to circle this force right here. If that says slab on block, right? So that means the slab is pulling the block to the left. If the slab pulls the block to the left, then the block pulls the slab to the right. So this is force of block on slab. Okay, same magnitude, just opposite direction. That's Newton's third law. The unsung hero, I think. Calculate V final. Oh, okay. Well, does it say there's friction blocking the slab? No friction between the slab and the table. That means that if there's no external forces, that means momentum's conserved, right? So we can conserve momentum. So let's do mass of the block, V naught equals mass of the block plus mass of the slab, V final. In the interest of time, I'm just going to tell you that if you plug those numbers in, I did it earlier somewhere. 0.57 meters per second, 0.57 meters per second. Okay, calculate the distance the slab has traveled at the moment it reaches V final. Well, you can do acceleration equals sum of forces over mass. And we just said that well, if you're the slab, okay, distance the slab has traveled, the only force acting on the slab is the friction from the block, right? So that would be minus mu normal over mass of the slab. And I was vague with my normal. I didn't put my subscripts because I did it intentionally, because this is the friction force on the slab, right? But I'm arguing that the friction force on the block is the same magnitude. So why don't we just use that one because it's easier to calculate? So minus mu normal on the block over mass of the slab. But look over here, this beautiful force diagram we drew. You can see that the normal and the force of the earth are the same. So it's just mg in this case, not always. Mu mass of the block g over mass of the slab. And then you can get the acceleration. It's 0.333 meters per second squared. And it's forward, right? Isn't the block pushing the slab forward? So it's positive. Interesting. Calculate the, oh God, the work done by friction. Calculate the energy dissipated from the friction force. I think that's what they meant to ask. So that would be 1/2 mv squared. And you would do on the slab, right? So how much energy was dissipated in the slab? It was transferred into internal energy. So it would be 1/2 the mass of the slab, which is 3 times 0.57 squared. And I did it earlier and I got 0.487 joules. Okay, so there's that. And that was a little bit rushed. Sorry about that. But I just wanted to make sure and give you homework. I know it's your favorite part. So easy. It's so easy after what we've done today, honestly. I almost feel guilty giving you such easy homework, but this is what it is because we did such a hard problem today. I'm just going to give you some nice, breezy, easy homework. Okay. So when we meet again, we're going to talk about the conservation of momentum. I hope you all stay home and I hope you stay safe. I'll see you soon.